Hey Chem 30, welcome to your lesson on spontaneity of redox reactions and how to build redox tables. So what are we talking about? Well, we're talking about knowing if a redox reaction will actually happen by considering the oxidizing agent and the reducing agent and seeing if they will actually react. We're also going to use our rules for figuring out if a reaction will happen to build redox tables. So redox tables are tables of reduction half reactions where we have the strongest reduction half reaction, so strongest oxidizing agents at the top, and then the weakest at the bottom. But you will see that as we go through. So here are the objectives for today. Compare relative strengths of oxidizing and reducing agents using empirical data, so our observations. We're going to try that out. We can't do it in real life because, you're stuck at home. And then predict the spontaneity of a redox reaction based on standard reduction potentials and compare their predictions to experimental data. And write and balance equations for redox reactions in acidic and neutral solutions by using half-reaction equations obtained from a standard reduction potential table. So those are the outcomes we are covering today. Anyways, to start off, what is actually happening when we have a redox reaction? Well, essentially what's taking place is that we have, and I want to get a pen going here, so give me a second. We have an electron being transferred, yes? So we have essentially the oxidizing agent is going to gain an electron, right? Because we have gain electron reduction happens to the oxidizing agent. So it's taking an electron away from the reducing agent, which is going through oxidation. So I have my OA, which is taking an electron, or more than one electron, from the RA. So in terms of figuring out if a reaction will be spontaneous or not, the question is the OA strong enough to take electrons away from the RA? And that's the question we're trying to ask. This isn't money, this is electrons. Okay, so that's kind of what we're trying to figure out when we figure out if a redox reaction is spontaneous or not. So here's a video, and let's think about, while we're watching this very pixely, bad resolution video, is this reaction spontaneous or not? So how do we know that a reaction is actually spontaneous? And if I take a look here, oh no, oh, a disaster. Okay, there we go, we're back. I'm going to go ahead a little bit so we can actually see. What's happened is we've put copper inside of what is silver nitrate. And as time goes on, you can see that I actually get this silver on the outside of the copper. So we can see that a new product is being formed. We're getting this new solid that wasn't present before. Then another thing we're going to see as time goes on is actually that we have this blue solution indicating that copper 2 ion is present. So we have both a color change as well as a new solid forming. So we know a reaction is happening. So the answer is yes. Yes, this reaction is in fact spontaneous. And what is happening here is that the electrons are essentially being lost from copper and they are going to silver ion to make solid silver. So we're going to take a look at the reactions in a bit. But what is happening to the electrons in this reaction? They are moving. The electrons are going from Ra to the OA. Okay, so the oxidizing agent is strong enough to pull the electrons away from the reducing agent. So that's what we're looking at. We're looking at the OA compared to the RA. So this is a reaction that you actually just saw where two silver ions are reacting with one copper atom, essentially, in order to give us two silvers and one copper 2 ion. So in this case, the OA of the silver is strong enough to actually pull electrons away from the RA of the copper. And in the process, the silver ion gets reduced and gains electrons to become solid silver, while the copper gets oxidized and loses electrons to become copper 2. So at this time, normally what would happen in the classroom is you actually would go around and try some reactions. So you would mix some solids with some nitrate solutions of different ions, and you would see if the reaction happened. So for example, you would mix solid zinc, so a piece of zinc, with copper-2 nitrate, and you'd see if the reaction happens, and yes, it does. And then you try solid zinc with lead-2 nitrate, and oh, that happens as well. But when you try lead with zinc nitrate, that reaction does not take place. So that would be the lab that would take place. Now let's quickly take a look, and you try to figure out, is the top or the side the OA, the oxidizing agent? So in other words, which would get reduced? Would the top things reduce, copper-2, lead-2, zinc, and silver? Or would the side elements get reduced? Okay, so the answer is, if you want to pause it now, pause it if you're still thinking, that these are my OAs up here, right? These are the things that would gain electrons, okay, and they'd get reduced. So they're becoming more negative. Well, these guys right here, these elements, would be my RA. They would end up losing electrons to become more positive, right? So poo, they're becoming more positive, it's oxidation. Therefore, they are the RA. Remember, the agent is the opposite of the process it goes through. So the reducing agent goes through oxidation, the oxidizing agent goes through reduction. Okay, so now that we figured that out, the next question is, well, what is the strongest oxidizing agent that we have? Well, because my oxidizing agents are again on top and my reducing agents are on the side here, I want to figure out, okay, well, which one is the strongest oxidizing agent that I had that got reduced? And the thing that ended up actually being the strongest oxidizing agent was the silver ion. It reacted with 1, 2, 3 things, right? So that is my strongest OA. So if I were to actually put half reactions in order from strongest to weakest, I would put the silver at the very top because it is the strongest oxidizing agent. So this is the strongest reduction half reaction that I have. The next one, number 2, would be copper-2. It is the second strongest reduction half reaction that I have. So in other words, copper-2 is the second strongest OA, and I know that because it has 2 yeses. It reacted with two different things. Next would be lead-2. It reacted with 1 thing. And then finally, poor zinc ion was just the worst OA in reacting with only 1 or 0 things. Sorry, it didn't react at all. Now my kids are fighting in the background, so it's hard to be too on with this. All right. Now what you'll notice is that actually by doing this, I end up creating this system where I actually have the strongest RAs at the bottom right. So if I consider RAs for zinc, zinc reacted with 1, 2, 3 things. It was the strongest reducing agent. Lead reacted with 2, copper 1, and silver none. So we kind of have this system where the strongest OA is at the very top left when I do reduction half reactions, and the strongest RA is at the bottom right when looking at reduction half reactions. That's really important. So this actually brings us to our spontaneity rule. We know a reaction will happen if the OA on the left-hand side of a reduction half reaction table is above the RA on the right. If it's downhill, then it's a spontaneous reaction. So you're going to actually build reduction half reaction tables, but you're also going to end up using the one in your data booklet a massive amount. Skipping ahead a bit, on page 7, you actually have this reduction half reaction table where you'll notice it's reduction because electrons are a reactant, right? So you have all this different information for different oxidizing agents and the reduction half reaction that they go through. Huge table. The higher up we are on the left-hand side, the stronger the oxidizing agent. So the strongest oxidizing agent on this table is fluorine, F2 gas. Okay. If we went to the very, very bottom right, we would find the strongest reducing agent in the whole table. So going back one slide here, let's talk about the spontaneity rule. The OA will be on the left-hand side of the reduction half reaction table, the redox table, and the Ra will be on the right-hand side. If the OA is above the Ra, I'm going to switch pen colors here. If the OA is above the Ra, it will be a spontaneous reaction. The reason why is the OA is strong enough to pull the electrons away from the Ra. It's stealing electrons from the Ra. It's like a bully taking away lunch money. Okay, the OA takes electrons from the Ra. If the OA is too weak to take electrons from the Ra, in other words, it's an uphill, then it's non-spontaneous. The reaction won't happen because the electrons cannot transfer. The OA is not able to pull the electrons away from the Ra. I want you to think about this as kind of like a sled. Yeah, so this is a hill. Here's a toboggan. See, it happens. It's fun time. Yay, going down the hill. This is not fun time. This is uphill. Okay, so non-spontaneous, spontaneous. Okay, so moving forward. Let's take a look at a few of these reactions on the table that we have here, and you can follow along in your data booklet and see if they're spontaneous or non-spontaneous. Let's do the first one. Oh, and I'm realizing that I have ones here that I cannot see on the table. So why don't we actually try doing a few that are just made up, and then you can take a look at this. I'm going to actually pause this, go to the table, and then figure out which ones are spontaneous and not spontaneous. So let's say that we were taking a look at, for example, chlorine and water. Okay, so I have chlorine reacting with water. So like in a swimming pool, for example. So the question is, well, is this a spontaneous reaction? Yeah, it is. I'm going to have a downhill reaction, so chlorine will react with water, and as a result, I would make chloride ions, and then I'd also get oxygen gas and hydrogen ions as well being produced. So because my OA is above my Ra, this would be a spontaneous reaction. It would take place. Now, what if instead I had bromine reacting with water? Well, in that case, it's uphill. It's going up. My OA is lower than my Ra. So my bromine is not strong enough to steal electrons from the water. Now, when you're looking on this table, as a side note, you need to find the thing it's saying here. So you need to find Al solid, bromine is Br2 liquid, but the coefficient doesn't matter. So it could have any coefficient, but it does have to be the exact same state, and if it's an ion, the same charge. Okay, but the coefficient, we're going to deal with those things later. All right, so why don't you take a look at your data booklet, figure out if these reactions are spontaneous or non-spontaneous. I'm going to pause this. I'm going to grab my data booklet, okay, and get it kind of like on a different screen or on this screen, and then we'll come back and we'll take a look and you'll see what the answers are. All right, pausing now. And we're back. So we're now going to try this out and show the spontaneity of these things as I go through. So to start out, when I have aluminum and bromine, so I'm going to actually underline this here, and hopefully you tried this out as well as you went through it. So aluminum is right here. Bromine, we actually just kind of pointed out before. So there's my bromine, there's my aluminum. I would actually write down too exactly what it is right here so we know that we're looking for the correct thing. So it'd be Al solid and Br2 liquid for bromine. So hey, that is very much downhill. That's a steep hill. Oh, that'll be fun to toboggan down. So we know that this is in fact spontaneous. Okay, so this will happen. That reaction would take place and we would make as a result aluminum bromide. We're not working right now on making the net reactions. That's the next thing. We'll be doing that, like next day that we have class. But right now, we're just focusing on the fact that, hooray, we found out that it is in fact spontaneous. Sorry, I should have turned off my email notifications. Next, copper-2 ions in solid gold. This is Cu2 positive aqueous for copper-2 ions. And then solid gold is, of course, Au solid. So let's track down where these things are. For copper-2, I'm going to find that right here. Hooray! And then for solid gold, I'm going to find that way up here. Now, actually, this is interesting. Gold is a really weak reducing agent. That's why gold is amazing and stays actually as solid gold, is because it is very, very bad at losing electrons. In other words, it holds on to its electrons very, very well. We call it a very noble metal because of the fact that it is so high up on the right-hand side, so it is a very weak reducing agent. Now this is uphill. Yeah, left is way lower than the right. That is no fun for tobogganing. So this is non-spontaneous. Okay, finally, iodine with calcium. I've got I2 solid, and calcium is Ca solid. So if I take a look, and I should erase this first, at I2, I2 is right here, and then I have calcium somewhere on the right-hand side. Oh, there it is, way down there. This is definitely spontaneous. Look at how downhill that is. Fantastic. So I know that this is a spontaneous reaction as well. Okay, so that is our table and how to use it. You just have to actually find the things that you have and then figure out if it is spontaneous or non-spontaneous. As a note, when I have these things that have more than one reactant, like for example, let's say this permanganate ion and hydrogen ion as well, I need to have both of those things in order to have that oxidizing agent. So everything that's on the left-hand side, I need to actually have as a major entity. But again, we're going to talk about this when we talk about predicting redox reactions next day. Okay, we can use this to build reduction half reaction tables. So we can actually build our own redox tables if we're given data about reactions based on that spontaneity rule of the OA is above the RA if the reaction is spontaneous, and the opposite is true if the reaction is non-spontaneous. And I'm realizing now when I use my hands, it's a mirror image, so don't use that for left and right. If you're a left and right confused person, which I've had in Chem 30 before, what you can do, and this sounds so silly, but try to make an L with both of your hands. And the one that actually makes an L between your index finger and your thumb, that's your left hand. That's the left one. All right. Anyways, we're going to get into now making these redox tables. So if I have CO2 positive aqueous and indium making ion3 positive and CO solid, and that happens, what I know with this is that my OA is above my RA because it was spontaneous. So my first step is figuring out, okay, well, which one was my OA? Well, copper 2 ion is the OA because that got reduced. That got more negative, right? So again, more negative, it's reduction. Well, indium became more positive, so that's oxidation. Poo. So that's my RA, reducing agent gets oxidized. So because this is spontaneous, I know that CO2 positive aqueous, I'm going to redo that, I want more room. CO2 positive aqueous is above IN solid. Now when I do this, my OAs are always going to go on the left and my RAs are always going to go on the right. Okay, I've covered this reaction. Now I've got copper 2 and cobalt. Now cobalt I actually know is over here, yeah? And I know that it's over here because cobalt 2 turns into cobalt. I can complete the half reactions later, but this is the same line because it's the same thing, just ion versus element, right? I don't want to say same thing, but you get what I mean. So now that I have cobalt 2 and cobalt here, I know that copper 2 must be above it because therefore it is a downhill spontaneous reaction. So again, for the first one, downhill, spontaneous, and then second one, also downhill, spontaneous. Finally, and now I've realized that I have definitely screwed up with spacing, so I'm going to have to do some fancy selecting of stuff and moving it down. Ta-da! Okay. Finally, for copper 2 and palladium, there was no reaction. So copper 2 must be below PD. This is my OA, and this is my RA. So copper 2 must be below, and then PD has to be above it. This is uphill, therefore non-spontaneous. So I have copper 2, I'm going to complete my half reactions now, plus 2 electrons, gives me Cu solid. How do I know it's turning to copper solid? Well, I can actually see that just right over here. I have cobalt 2 positive plus 2 electrons gives me CO solid. Again, I can see that that's what it forms from the first reaction. Palladium, I'd have to look that up, right? Because I don't actually have the charge for that, but on the periodic table, it's PD2 positive aqueous plus 2 electrons gives me PD solid. And finally, for indium, I have the charge for that. It is 3 positive, so IN 3 positive aqueous plus 3 electrons gives me indium. Now again, these are reduction half reactions. You'll notice that in all of these, electrons are to the left. It's gaining electrons because that is the definition of reduction. I can double check my work now and make sure that if I were to look at the reactants again, it turns out how it should for spontaneity. So cobalt 2, indium, hey, that's downhill, it's spontaneous. Copper 2, cobalt, hey, that's downhill, it's spontaneous. And then copper 2 and palladium, oh, that's uphill, that's non-spontaneous. So I can double check my work after the fact. Okay, here's another format that we can actually use. In this case, what I've done is I have left no products, and what that is telling you is that it is non-spontaneous. So in other words, the products didn't form, so I'm not writing them. So the first two reactions I'm showing here are spontaneous. The other two, the next two, are non-spontaneous. What I'm going to have you do is I'm going to have you pause the video, try labeling all of the reactants as OAs or RAs, right? Each reaction will have one OA, one RA in the reactants. Take a minute, try to label OAs and RAs. We're going to pause and I'll be right back. Okay, so here's the OAs and RAs. If I take a look at cadmium, it's becoming more negative, right? It's getting reduced, so this must be the OA, while beryllium is becoming more positive, so poo, it's getting oxidized. That makes it the RA. For hydrogen, it's positive, it's becoming more negative, going to a charge of 0. So this is getting reduced, right? So this is my OA, it's nurring. While cadmium is getting more positive, so it's getting oxidized, poo. So that happens to my RA. Calcium being a positive ion, the only thing it can do, because calcium is not multivalent, is it would get more negative, becoming an element. So that's reduction, so that happens to the OA. Well, beryllium then would be the RA. Once I've identified the one, I know the other, right? So that is a shortcut as well. And then hydrogen ion would become more negative, so it gets reduced, so that's the OA. Well, copper would end up getting oxidized to become more positive, poo, which is the RA. All right, so now let's actually try making my redox table. I like starting somewhere in the middle just so I have some room, unlike where I ran out of room last time. So we're going to start a little bit lower so we can make sure that we have the room to plan around going up or down, because we don't necessarily go down with each half reaction or up with each half reaction. It depends on where it places with the other one. So I'm going to start out with my OA, right? OA always goes on the left. I have CD2 positive aqueous. And this reaction happens, so I know that beryllium, Be, is below it. It's downhill because it was spontaneous. Why don't we right away actually just finish up these half reactions so we have them. So I have 2 electrons being added, making CD solid. For beryllium, I have Be 2 positive aqueous plus 2 electrons makes Be solid. Okay, so that's my downhill. Going to the next reaction, I have cadmium and I have hydrogen ion. So I have this as my RA, 2H positive is my OA, and that happens. So I know that H positive has to be above this reaction in order for me to get, again, a downhill spontaneous reaction taking place. So 2H positive aqueous plus 2 electrons gives me H2 gas. Okay, so this one's done. Now, calcium and beryllium, that doesn't happen. So here's my RA, yeah, and then calcium has to be below it in order for it to be uphill. So calcium is going to be right here. Calcium 2 positive aqueous plus 2 electrons gives me Ca solid. And then I have finally copper and 2H positive. This doesn't happen. So therefore, it must be actually a downhill or uphill, sorry, reaction, non-spontaneous uphill. So what that means is that it has to actually be above hydrogen. So copper needs to be somewhere right here. Cu2 positive aqueous plus 2 electrons gives me copper. Okay, now I like to go and double check and make sure that everything matches what it should. Let's go to a different color here and talk through it and see that it matches. We'll go with yellow. So Be, right, solid in cadmium, that's downhill, that's spontaneous, and that matches my data. Okay, cadmium and 2H positive, that is also downhill, so it's spontaneous, that matches. Calcium ion and beryllium, that is uphill, so it's non-spontaneous. And then finally, copper 2 and hydrogen ion, copper solid and hydrogen ion, that is uphill, that is non-spontaneous, so that matches this reaction as well. So just good double check to make sure that everything does match our original reactions to make sure we're on track. All right, in your workbook, you have some questions. I think it's a good idea for you to try out. I've got here one, wait for it. Oh, I'm screwing up my controls here. I have number 1, I've got number 3, and I've got number 6 in these slides. I thought that would give us a good kind of mix of different ones in increasing difficulty. So from this point on, what I'm doing is actually going through some of the answers from the key, because I think it's really beneficial for you to see those answers happen. So if you want to stop watching right now because you're good, hey, fantastic, that's great. If you are still needing some help, I would suggest trying these questions first, yes, and then after you've tried it, come back and see if you did the process correctly or made sense of it. Anyways, let's go through number 1. A little bit less explanation from me for these because we've already gone through a few. So first of all, I want to get to a proper color here. We'll go back to red. All right, so PD2 positive is an OA, right, because it's becoming more negative, reduced. Cobalt is an RA. PT2 positive is an OA. PD would be an RA. And then cobalt here is an OA, and magnesium is an RA. So all of these are spontaneous. So for the first one, I know that PD2 positive aqueous is going to be above cobalt. It's downhill because it's spontaneous. And then I have PD solid across from that. And PT2 positive as an OA is uphill. So I have PT2 positive aqueous up here going downhill to PD solid. So it's spontaneous again. And then finally, I have magnesium and cobalt 2. So cobalt 2 positive would actually be across from the cobalt solid. And my magnesium is down here because it is, again, downhill. In other words, a spontaneous reaction. So plus 2 electrons, plus 2 electrons, plus 2 electrons makes PT solid. So just finishing up my half reactions. And magnesium has a charge of 2 positive aqueous, which we can see in the products of the last reaction or our periodic table. So this is my reduction half reaction. So the strongest oxidizing agent that I have in all of this is actually PT2 positive. So this is my strongest OA. And the strongest RA from the data that I have is actually magnesium. This is my SRA. My weakest RA is platinum, solid platinum. My weakest OA is magnesium ion. All right, question number 3. The hydrogen ion is my OA, my platinum is my RA, the nickel 2 is my OA, the cesium is my RA. I have this being my OA, strontium is RA, and then again OA and RA. Unfortunately with this one, it's all in the same order, which is actually kind of too bad. I like when it's mixed up for a better example, but it is what it is. All right, so I've got 2H positive aqueous, and I have a non-spontaneous with platinum. So I know that platinum is somewhere above it because it's an uphill non-spontaneous according to the thing that you can't quite see. You can see the non. You know what's going on. All right, next I have cesium and nickel 2. Now, this is great. This brings us to a good example. I don't have either of those here. So I'm going to skip it, move on until I have something that I have already on my table, and then I'll come back to them later on. I don't have anything from the third one either. So actually, I go all the way to the last reaction where I have 2H positive, I have nickel, so I'm going to have Ni solid down below it because it's spontaneous. Let's go ahead and finish up what we already have here. Ni2 positive aqueous plus 2 electrons gives me Ni solid. I have 2H positive plus 2 electrons gives me H2 gas. If you're confused about these half reactions, rewatch the half reaction video, yes? I'm each time just making sure that my charge is equal on both sides. So I'm adding electrons to the more positive side to make the charge equal for both. For the top one, I had PT2 positive aqueous plus 2 electrons gives me PT solid. Oh, this is a messy table. All right. Now that I've done that, I can go back to my second reaction because I now have nickel 2 and I have cesium, and it turns out that that is spontaneous, so Ce has to be below. Okay, so I've got Ce2, no, 3 positive aqueous plus 3 electrons. So that's now done. And then if I go to the second reaction, I have Ce and nickel 2, and that is spontaneous. Oh, no, that's what I did. Oops, third reaction, my bad. C3 positive strontium, that is also spontaneous, which means it is downhill. So I have Sr2 positive aqueous plus 2 electrons gives me Sr solid. Let's go into our double check mode. We're going to use green. So I have PT and hydrogen, that is uphill, non-spontaneous, check, that's great. Cesium, nickel 2, that's downhill, spontaneous, check. I have strontium and Ce3 positive. Hey, that's downhill, right? So that is happening, spontaneous, good. I have nickel and hydrogen ion, so I got nickel, hydrogen ion, boop, downhill, so that is spontaneous. You'll notice that I have spontaneous, spontaneous, spontaneous for my downhills, and I have non-spontaneous for my uphill. So it all checks out. Beauty. Okay, now last one, and this is by far the most complicated one. We got a good mix of different things going on here. So R2 positive, that will be my OA. X will be my RA. Q2 positive will be my OA, more positive again. X is again my RA. Here I have an X2 positive, that's going to be my OA as a positive thing, and then M is my RA, and then Q2 positive is my OA, and M again is my RA. Actually, I was really hoping that there would be ones with non-metals in here, but it is what it is. Okay, so what we're going to do is we're again going to start with R2 positive. My first reaction, I shouldn't say again, we haven't done this with R2 positive before. What's neat here though is these aren't elements that we have on the periodic table, it's just made up. So we have to be a little bit more careful that we get the right charges and we build our half reactions properly based on that. So R2 positive and X, that is spontaneous because I have products listed, so therefore it is a downhill to here, so I'll just put X solid right there. Then I have Q2 positive and X, and that doesn't happen, so that means that my Q2 positive would have to be below my X, so I'm going to put it here. Okay, so there's my Q2 positive. I have X2 positive, which would be opposite of my actual X and M, and that happens, so that's downhill. It's somewhere here or here. I don't actually know which one, but then I can figure that out from my fourth one, where Q2 positive and M ends up actually being no reaction. So I'm going to put my M right here, and let's see if I can actually move some stuff around. Ah, beautiful, in order to make that work. So now I can complete my half reaction. So R2 positive turns to R, as I can see in this first reaction. So 2 electrons gives me R solid. X2 positive plus 2 electrons gives me X solid. When I look at the M, I know that it's 3 positive for a charge. I can see that right there when it's in its ion form. So M3 positive aqueous plus 3 electrons gives me M solid. And then Q2 positive plus 2 electrons gives me Q solid. All right, going into double check mode. Let's use red, it's Christmas. All right, so I got R2 positive in X, that is spontaneous, it's downhill, which matches what I have here, that I have reaction or products listed, sorry. Q2 positive and X, here's my Q2 positive, here's my X, that's an uphill, so non-spontaneous, which matches what I have here of no reaction. Then I have X2 positive and M, that is downhill, so spontaneous. Hey, I got products, that's great. And then finally I have Q2 positive and M, which is uphill, yeah, no reaction, which again matches what I have there. So we have, oh,